Hello students, today we will be seeing relation and functions theory. A small disclaimer. The images, text and other materials used in our presentation are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the same. Thank you. So what we will be covering in this session is about function, then real valued function, identity function, constant function, polynomial functions, rational functions, the modulus and signum function, greatest integer function, and other types of function like a 1-1 function, onto function, bijective functions. So starting with first function definition. So your f must be a relation, first of all, a relation f from a set A to set B. So you are having a relation f from a set A to set B. And it is said to be a function if following certain conditions, if every element of set A has one and only one image in set B. Meaning every element must be associated to some element and that element must be unique. We cannot have that any element from set A is being associated to two elements of set B. No, we only want one and only one image for an element of set A to set B. In other words, F is your relation from a non-empty set A to non-empty set B such that the domain of your relation F is A and no two elements, no two distinct ordered pairs in F have the same first element. So if you are talking about in terms of ordered pairs, you know your relation is just some collection of ordered pairs following certain condition. So we want what? That the domain of the relation F must be the complete set A. First thing. The second thing is that if you pick any two ordered pair from your relation set, then if they are distinct, then they do not have first element same. If you are seeing such order pair in which the order pairs are different but having the same first element, then in that case you will say that your given relation is not a function. I hope it is clear up till now. If not, don't worry, we will be seeing bunch of examples and it will be all clear then. If f is a function from A to B and A comma B pair belongs to this relation F, then we say f input A is equals to B. Meaning B is your image of A under F, and A is called pre-image of B under F. These are some terminologies that we are going to use. So image meaning, so B is your image of A under F. So this output element will be your image, while this input will be your pre-image. Or you can say that the first element will be your pre-image and second element will be your image. Clear? And we denote a function from A to B like this. F is a function with domain A and codomain B. This we call it domain of relation F, or in this context function F, and this set will be a codomain. Clear? Now some related example. Suppose n is a set of natural numbers and the relation R is defined on set of naturals such that, so this is your set builder form of your relation R. Collection of all pairs, ordered pairs x comma y, such that y is equals to twice of x and x and y both belongs to set of naturals. Simple. So now in this question or in this example, we are asked to find out domain, codomain and range of R. Is this a relation function? Simple. We are having three questions. So domain, codomain, R and about function. So we have to answer all of these three. Simple. So how we are going to start? Very simple, by definition. So starting with the set builder form of the given relation, set of all ordered pairs x, y such that y is twice of x and x, y both belongs to set of naturals. Now we have to answer for domain, codomain, range of R, and is the given relation a function? So solution. So if you recall, the domain definition is nothing but collection of all first element from the ordered pair belongs to the relation R. Simple. Codomain. Codomain is simply this, the set from where your second elements belongs to. Simple. So here domain is simply your what? Set of natural numbers. Why? Because your first element, which is x belongs to what set? Naturals. So it is what? Your domain set. Now for codomain y, we have to see that this y belongs to what set? So y also belongs to the set of naturals. So codomain is also naturals. Simple. Now we have to carefully observe that this y is of what form. In order to get the range, we require collection of all y's belongs to, or simply collection of all the second elements of the pair, and these pair belongs to the this relation R. So you know that this y must be of the form twice of x. Yes, and meaning x belongs to set of natural, so twice of some natural number. So you will get twice of some natural, meaning even natural number. So range will be simply your set of even natural numbers. Clear? And keep one thing in your mind, that range set will always be your subset of your codomain set. Always. If codomain and range set same, then in that case you will be seeing that this is some kind of special function. For now, just focus on that range will always be your codomain's subset. Now, in order to say it is a function or not, what we need to verify is simply that for every element from domain, we must have an image. Yes? So every natural number n has one and only one image. So satisfying the condition of the function. So this given relation is a function. Clear? Now another example. Examine each of the following relation given below and state in each case given reasons whether it is a function or not. So relation R with roster form given to us, 3 pairs 2, 1, 3, 1, 4, 2. Second relation with pairs 2, 2, 2, 4, 3, 3, 4, 4. Third relation with pairs 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. So simply we just have to verify that among the given 3, which satisfy the function definition or not. So first, second and third, meaning 3 relations are given to us in roster form. Solution. Since 2, 3, 4 are the elements of domain of R having their unique image, this relation R is a function. So simple, if you consider your domain as 2, 3, 1, then you can easily see for every element in domain you are having unique image. So 2 related to 1, 3 related to 1, 4 related to 2. No two distinct pair having the same first element. Clear? So satisfying the function definition, so it is a function. For second, if you observe, these 2 pairs are distinct indeed. Why they are distinct? Because the second element not same as this second element. So we consider such pairs as distinct pairs. Now, but here we see that the first element from both the pairs same. So it contradicts or not satisfies the condition. So not a function. For third, domain 1, 2, 3, 4, 5, 6. And you see that every element from the domain is associated to an image. And one and only one image. So satisfying the definition, so a function. I hope it is clear. Now, real valued function. A function which has either R or one of its subset as its range, we call it as a real valued function. Clear? So a function which has either R meaning the whole real number, so set of whole reals, or one of its subset as its range, then we will be calling such function as real valued function. Simple. Further, if its domain is also belongs to a subset of reals or the complete real, then we will be calling such function as a real function. So in real function, domain as well as codomain belongs to the set of reals, while in a real valued function, the domain, the range must be a subset of reals. Clear? Now, identity function. Let R be the set of real numbers. Define the real valued function f R to R. Y is equals to fx is equals to x for each x belongs to R. So such a function is called the identity function. So simply the whatever the input, the output is the same. So fx is equals to x. So if you plot the graph for y is equals to x, you will get a straight line passing through origin, as you can see. And how you are going to plot this? Very simple. Just put x1, then see that output will be what? 1, same as the input. So putting x2, you will get uh, output as 2. So you will get 2, 2, 4, 4, 6, 6, these pairs, and just join all these points, you will get your straight line. As you can get the same output, same as input for every x belongs to the real number. Clear? Now for constant function. So defining function from R to R, y is equals to fx is equals to c, where x belongs to reals and c is your any constant. Simple. So this represents your what? Domain set. This represents your codomain set. Here plot the graph will be like this. So this is when we are considering c as 3. So fx is equals to 3. So constant function. So constant function graph will always be parallel to x-axis or overlapping the x-axis when fx is equals to what? 0. Clear? Now polynomial function. A function f R to R is said to be a polynomial function if for each x in real we have fx is equals to a0 plus a1x plus a2x square till an x raised to power n, where n is your non-negative integer and ai belongs to the set of reals. Such form you will be calling it as a polynomial function. So example, so simple, this parabola. So graph is parabola, but if you try to see, fx is some x square. Clear? You can easily plot your graph. If you put input 0, output will be 0, so 0, 0. If you put 1, the output will be 1, so 1, 1. If you put 2, then output will be 4, so 2, 4, and so on. And you will join your points, your pairs, and you will get this sort of curve. Clear? Now rational functions. Function of the type fx by gx, where fx and gx both are polynomial functions, and we just saw what do we mean by polynomial functions. Obviously we do not want our denominator to be 0, so we require the condition where gx cannot be 0. So for example, fx is equals to 1 by x. This is your, so fx is some fx is 1 and gx is x, both polynomial functions. And obviously we do not want our denominator to be 0, so x cannot be 0. So in domain we eliminate such points where denominator becomes 0. Simple. Clear? So domain for this function fx is equals to 1 by x, domain is complete, not complete R. If you eliminate 0 from the all real numbers, then the domain will be R minus 0. Clear? Now modulus function. Simply function defined from R to R, defined as fx is equals to mod x for every x belongs to the reals. We call it as a modulus function. So for every non-negative value of x, fx is x, but for negative value of x, fx is negative of x. Mathematically, we are saying if fx is 0 when input is 0, fx is x when input is positive, any positive real number, and fx is minus x when input is negative. One liner, mod x denoted by this mod x, but piecewisely it containing this much of information. Graph will be, if at 0 the output is 0, so 0 comma 0 pair. At any positive real number you will get the same real number. So at 2 you will get 2, at 4 you will get 4, and so on. Join them, you will get your line. Any negative number, the output will be minus of the negative number. Meaning if you put minus 1, the output will be what? Minus minus 1, meaning 1. So if you put a minus 2, then output will be plus 2. So at minus 2, output is plus 2. At minus 4, output is plus 4, and so on. Join them, you will get your this line. So complete graph will be like V, and this vertex at 0 comma 0. Clear? Now signum function. So signum function defined from R to R. Fx is equals to 0 when input is 0, fx is 1 when input is positive, any positive real number, and fx is negative 1 when input is any negative real number. Graph will be, at 0 you will get 0 comma 0 pair. For any positive real number the output will be 1, so 1. This small circle at 0 represent that at 0 we do not have y1. Clear? The same goes for this. For any negative x you will get output as minus 1, so your line will be like this, and this small circle represent the whole, meaning at 0 we do not have minus 1 output. Clear? In terms of modulus you can also rewrite it as fx is equals to mod of x by x, where obviously we want denominator not to be 0, so x cannot be 0, so we have to explicitly define for 0. So for x 0, f is 0. Clear? And these functions, modulus, signum, real valued, the identity, constant function, all are real valued functions as domain as well as the codomain subset of your reals or real itself. Now greatest integer function. So simply defined from R to R, denoted as a box x, and this gives what it actually represents is value of greatest integer less than or equal to x. Simple. So this gives you value of greatest integer less than or equal to x. Such a function is called a greatest integer function. For example, if you consider, so suppose input is 1.5. Now think of integer less than 1.5. You can easily think 0 is less than 1.5, 1 itself less than 1.5, 2 no, 2 is not less than 1.5, minus 1 less than 1.5, minus 2 less than 1.5. So you can list infinitely many integers less than 1.5. But this represents the greatest of the greatest integer less than or equal to 1.5. So greatest is 1. So for 1.5 the output is 1. So as you can see, so 1.5 will be somewhere here and the output will be 1, as you can see 1. So if you pick any real number from open interval 0 to 2, the output will be 1. Even if input is 1, the output is also 1. Clear? So the graph will be like this. This is your floor function also. So another term for this is floor function. So as you can see, staircase, floor. Clear? And this little circles represents what? At suppose this circle. So at 3 we do not have output 2. So this little circle represent at 3, we do not have the output 2. Clear? So whenever you see these type of circles, there is open hole, you quickly conclude that at that specific point the output is not the given. Clear? Now we will be covering one function. What do we mean by one function, onto function, and bijective function? So starting with one functions. So your function f defined from x to y is 1 or another word is injective if the image of distinct elements of x under f are distinct. So the image of distinct element of x under f are simply distinct. Meaning, if you pick any two distinct element or just pick any two elements from your domain and find out the image, meaning fx1, fx2. If both images are same, then we must have x1 same as x2. Otherwise, your function will be many one. If you are facing that if you have two distinct elements from domain, but the image is same, then you will say your given function is many one. Simple. I hope it is clear. What do we mean by one function? If image is same, then we must have x1 same as x2. Otherwise, it will be all clear when you see different examples. Okay. Now onto function. Your function defined from x to y said to be onto, in other words surjective. If for every element of y is the image of some element of x under f. Simply, your codomain set is equals to the range set, then you will say that your function is surjective or onto function. Simple. So if you pick any element from codomain set, you must have a pre-image. They exist in x such that fx is equals to y. Or every element in this set must be associated to some element from this domain set. Clear? Now examples. It will be all clear from examples. So function defined from set of natural to set of naturals as fx is equals to twice of x. And this function is, we are saying it is 1 but not onto. Let's see how we are saying that fx is equals to 2x is 1 but not onto. Solution. So for 1 we start with what? We always start with x1 x2 and put f of x1 same as f of x2. So f of x1 is 2x1 and f of x2 output will be 2x2, both equals, and we can easily cancel 2 and we are having x1 is equals to x2. If you are having such case, if you are starting with fx1 is equals to fx2 and eventually you get to the case where x1 is same as x2, then you will say that your function is 1 without any hesitation. Now for onto, we want range to be same as codomain, meaning, or in other words, every element of this set must have pre-image. So if you observe, we know 1 belongs to the codomain set. Are we having any x such that 2x is equals to 1? No, we don't. In order to get the solution for this, we require x to be half, and half doesn't belongs to set of natural. So there does not exist any x in set of natural, so not onto. So we got an element from codomain set which is not associated to any element from the domain set. Simple. This example. So function R to R. Now we are considering from real to real. Fx is equals to twice of x. Now it is 1 1 as well as on 2. What happened here? So quite interesting thing is happening. So here we changed our domain and codomain to R. In previous example, we had natural numbers as a domain as well as codomain. While in here we are having real numbers as our domain and codomain. So the onto-ness and the 1 1 for any function to be 1 1 and onto, it is totally depending on the domain and codomain we are taking. Clear? So without domain and codomain, you cannot answer your given function is 1 1 or onto. So let's see how the given function fx is equals to 2x from R to R is 1 1 as well as onto. Solution. So for 1 1, always start with fx1 is equals to fx2 and try to find out the condition you are getting x1 is equals to x2 or not. If you are getting x1 is equals to x2 condition only, then you will say that your given function is 1 1, otherwise many 1. So starting with fx1 is equals to fx2, fx1 will be 2x1, fx2 will be 2x2, both equals, cancel 2, you will get x1 is equals to x2. So 1 1. Now in order to show this function is onto, we are required to show the range set is same as codomain set, or you can also show that for any element from codomain set there exists x belongs to the domain set for which fx is equals to 2x. Simple. So we are starting with y, taking y from codomain set. We are saying there exists y by 2 belongs to the domain set such that f of y by 2 is y. Yes? So hence f is your onto function. So what we have shown is simply we started with any element from codomain set and said there exists a element from domain set and the element is y by 2. If you such that the image of f of y by 2 is y, meaning this y is associated with y by 2. So hence it is onto. I hope it is clear. It will be all clear that how this is your first time, so don't worry. More example will be introduced to you in order to grab the concept of 1 1 and onto. So the graph for fx is equals to 2x for real to real. So pick any real number, you will have twice of it. So your graph will be straight line and passing through the origin. Clear? Another example, function n to n defined from n to n. Domain is n, codomain is also n. Then given by f1 is 1, f2 is 1 and fx is x minus 1 for x greater than 2. So function is defined in this manner. Is 1 onto but not 1 1. So you have to show that the given function is onto but not 1 1. Simple. So how you are going to start to show 1 1 or not 1 1? Very simple. If you can find any two distinct input having same output, then you will say that the given function is not 1 1. So solution. Very easy. It is already given that we know the output for 1 and output for 2 both same, but 1 is not same as 2. So it is not 1 1 directly. So we are having two distinct inputs where output is different. In such case, we say f is not 1 1. Now for onto. we have to show that it is onto, meaning we have to show if you pick any natural number from codomain set, it must be associated to some natural number in domain set. Let's see. So pick any y from codomain, natural numbers. Obviously, we do not want y to be 1, so y cannot be 1. Clear? We can choose x as y plus 1 such that f of y plus 1 is equals to y. Clear? So we are having, if you are picking any y from the domain set, codomain set, then we are having element from the domain set an element of the form y plus 1. Then we are having f of y plus 1 is equals to y, meaning y is associated to some element which belongs to the domain set. Why? We excluded 1 because 1 is already associated. As you can see, it is associated with 1 and it is associated with 2. Meaning, so that's the reason we excluded 1 here. Clear? Or if you try to observe that the domain set, not the domain, the codomain set and the range set is same. So if such the case, then you will say that your function is onto. So I hope it is clear. Simple. Now another example. So show from f r to r defined as fx is equals to x square is neither 1 1 nor onto. Simple question. So how we are going to show it is not 1 1 and not onto? Very simple. Just think of some counter example. For 1 1 you have to just think of any two elements from the domain having the same output, and for not onto we have to figure out some element in codomain set which is not associated to any element of the domain. Solution. So simply, if you put x1 the output is 1, and if you put x minus 1 the output is also 1. So image of 1 and minus 1 both same, so not 1 1. For onto, simple, in order to be onto we require range set is same as codomain set. If you observe here, this will be your positive output. This always going to be give you positive output, meaning you cannot have negative output, while in codomain set you are having negatives also, negative real numbers. So there's no x which can give you negative output. Simple. So if you pick -2 from codomain set, then there doesn't have any x such that x square is -2. So f is not onto. Simple. So by graph, how you are going to answer? Very simple. If you know the graph of any function, then for 1 1 you can easily perform horizontal line test. Meaning if you passing a horizontal line like this, and that horizontal line, if that horizontal parallel to x-axis line intersect your graph at 2 points, meaning you will have two distinct elements such that the output is same, so not 1 1. So horizontal line test gives you answer about 1 1 and not 1 1. Clear? And you can see that this function graph is like this. Yes, meaning covering all elements on y-axis. What elements? 0 to infinity plus infinity, while it is not covering the elements negative real numbers. But in codomain we already have negative. So domain, codomain and range set both different sets. So simply you will say that it is not onto. So from graph you can answer both 1 1 as well as onto. Another example, function defined from set 1 2 3 to set itself 1 2 3, and we have to show that if this function is onto. If it is already given that it is onto, then we have to show that onto function from 1 to 3 to 1 to 3 is always 1 1. Let's see solution. Suppose f is not 1 1. Suppose we are saying f is not 1 1. Then there exist two elements, say 1 and 2, in domain whose image in the codomain is same. Yes, if it is not 1 1, then we must have two elements from the domain set for which we are having the same output. So also the image of 2 under f can be only one element. Therefore, the range set can have at most two elements of the codomain 1 2 3, showing that f is not onto. A contradiction, hence f must be 1 1. I hope it is clear. Very simple. Now, suppose this function defined from 1 2 3 to 1 2 3 is given to us, it is 1 1 function, then we have to show that it must be onto. Very simple. Solution. F is 1 1, meaning 3 elements of this set 1 2 3 must be taken to 3 different elements of the codomain. Yes, so meaning we covered all the elements of the codomain set. So range set is same as the codomain set. So by definition, f has to be onto. Clear? Now a remark, the results mentioned in examples are also true for an arbitrary finite set x, that is a 1 1 function f x to x is necessarily onto, and an onto map from x to x itself is necessarily 1 1 for every finite set. Finite set means we can easily count the numbers of the elements. So it is in general true in context of finite sets. Clear? So in contrast to this, for an infinite set, this may not be true. In fact, this is a characteristic difference between a finite and infinite set. Clear? Now, bijective function. If your function is both 1 1 and onto, then such functions will be your bijective functions. Some important formula. So number of possible functions. So number of possible functions simply given by. So if you are having set A with m elements, set B with n elements, then the number of functions from set A to V will be n raised to power n. Simple. You can associate these n elements to m elements. Now for example, if you are having set A with 2 elements and set B with the same cardinality with 2 elements, then there are 2 raised to power 2, meaning 4 possible functions from set A to set B. You can easily directly use this form also, n raised to power n, where n and m both are same in this specific example. Now, what about the injective functions? So number of injective functions, another term is 1 1. So first condition must be that n is strictly greater than equals to m, meaning set number of elements in set A must be less than or equal to the number of elements in set B. Clear? Now, then we can easily find out the number of injective functions or 1 1 functions from A to B as n factorial by n minus m factorial. If you are curious about this formula, and this will be simply comes from permutation and combination concept. Here we are not going to discuss that. For now, just memorize this, as in exams this is very important. Now, what about surjective functions, meaning onto functions? If A and B are two sets having m and n elements such that n is greater than equals to 1 but less than equals to m, then number of surjections, surjection meaning onto functions. So we will have this much of a number of surjective functions, and this formula is also derived from the concept of permutations and combinations. So you just need to memorize this. Summation of r goes from 1 to n. Summation of what expression? Minus 1 raised by n minus r times n r. This nr represents your binomial coefficient. Simple. Times r raised by n. Clear? Now, what about bijective functions? If there is a bijection between two sets A and B, then we must have the cardinality of both sets same, meaning number of element in both sets must be same. So, n number of elements in A same as number of elements in B, which is m, then your number of bijective functions is m factorial. Clear? So this is it from this session. Thank you.